Okay, we're going to start talking about chemical energy. All right? So, when we talk about chemical energy, we use the term thermodynamics. It's basically the study of energy, heat, and work. It helps us to understand why some chemical reactions occur and why others do not. In thermodynamics, we can only measure the change in energy. We cannot measure all of the energy. It's not like we can hold up a 5-pound bag of sugar and say, okay, this is all the energy there is. All we can do is measure changes in energy, and most of the time we do that through temperature. We can never really measure all the energy in a system. All right, I use the word system, and here's another term, surroundings. And so let me give you an example of this sample A here. You see the system and energy is leaving into the surroundings. If you went outside and it was really cold and you could see your breath when you would blow, you would become chilled. And the reason you're becoming chilled is that the surroundings have low energy and you are a source of high energy. So if it's 0 degrees Celsius outside and you're at 98.6 degrees Fahrenheit, you have more energy. And so energy, just like anything else, moves from high concentration to low concentration. And so the heat energy moves from the system, you, to the surroundings. That's the universe around you. Okay? Same with a chemical reaction that we have in a beaker. If that beaker generates heat, that's the system, it will radiate out into the surroundings where you can feel it with your hands. The system is the thing where the reaction is taking place. Surroundings on this course, you see heat energy is going in. This is you. If you are the system, then in the middle of the dead of summer, when it's burning up hot outside and your air conditioner doesn't work, you are absorbing heat energy from the surroundings. Because it's 110 outside in the shade, you have lower energy than the surroundings. And so heat energy moves from high concentration to low concentration. And so your body temperature goes up. Okay? Same thing in chemical reactions. Okay. Let's just review a few of the rules of the kinetic molecular theory just really quickly. All right. Molecules and atoms in a reaction mixture are in constant random motion. Molecules and atoms frequently collide with one another. Only some collisions, those with sufficient energy, will break bonds in molecules, and when reactant bonds are broken, new bonds may be formed and products result. Okay, so the law of conservation of energy is the first law of thermodynamics. It basically says that energy of the universe is constant. So what does this mean? This is so basically what we're having to understand is if energy in the universe is constant, all it means is it's changing places, moving back and forth. And so where does the energy come from that is released, and where does energy go when it's absorbed? Let's see what we can do to help clarify some of this, all right? Here we have two reactants, AB and CD, and bonds are going to be broken and new bonds are going to be made. So A is joined now to D and C is joined now to B. When bonds are broken, energy is required. I don't know if you've ever played that game called Red Rover, Red Rover. And so you form two lines of people and they link their hands together and somebody tries to run over and break through the line. As long as the two people holding their arms together tightly and a little guy comes in, he doesn't stand a chance of breaking through the line and he gets captured. A bigger person comes through and they can break through the line. That's the same as breaking a chemical bond. When that person breaks those hands apart, a chemical bond is broken. Energy is required to break that bond. When we talk about reaction types, we're talking about endothermic and exothermic reaction. Remember, energy is required to break bonds, and energy is released to make bonds. So, if we have breaking bonds, if we put a lot of energy in to break those bonds, and new bonds are broken, and it takes less energy to make the bonds than it did to break them, then the system is exothermic. When those new bonds are broken, that extra energy has to go someplace and it's released to the surroundings. All right? Well, what's an endothermic reaction? Well, here's a good example. As you can see, this is an exothermic reaction, and you can see the flame and the smoke and the heat. The new bonds that are being made take less energy, and therefore that extra energy that the molecular model absorbed when it broke the initial bonds has to go somewhere. And as you can see, it's being released to the surroundings. Endothermic reactions. What does that mean? An endothermic reaction is just what it means, that energy has to be absorbed, and it's always based with the products. So energy was required to break the AB bond and the CD bond. But when A and D and B and C are formed, it takes more energy than what was absorbed. And so where does this extra energy come from to make these bonds? It comes from the surrounding. Energy has to come in. That's why endothermic reactions are cold to the touch, is because since it takes more energy to make these bonds, the energy supplied to break these bonds is less than the energy required to make these new bonds. And for that energy has to come from somewhere, and that's from the surroundings. Okay? And so here's an example of an endothermic reaction. We take this chemical mixture here, and we put a few drops of water on the top of this block of wood, and this water freezes. The energy required for the new bonds is insufficient from the energy required to break them, and so the energy has to come from somewhere to make the new bonds, and it comes from the surroundings. And this area between the block of wood and the bottom of this flask, that's part of the surroundings out here, and the energy is removed, goes from outside to inside the flask. The energy out here is removed. Energy is moving from the outside to the inside here and making this area cold. Energy is lost from the surroundings here, going to make these new chemical bonds, making this area cold enough to freeze water. All right. Well, thank you very much, and go ahead and work the example problems, and then we'll get started with the rest. Thank you.